Okay, I hope this time we'll arrive at some things where I really have to do something. That is, I'll have to spontaneously derive some proof, and I didn't mean proof of simple statements, but some proofs that require at least some technical thinking. So, well, let's see if we right here. So last time we have discussed the definition of linear maps, and we have discussed some examples, and we finished at a particular application which I didn't present rigorously but have still shown you, was the application of linear maps for the linearization of differentiable maps. Right there, finished last time. And now go on with the discussion of the notion that are important in the context of linear maps. Right. Um, well, what's that? Oh, yeah. Definition. Let's L, and we recall that V and W are just our K vector spaces as always. B linear map. Then we call this set kernel L. And this is the set of all vectors in V that are mapped by L to the vector 0 in W. So that is actually W, 0 in W, but we'll omit this because it's clear from the context which 0 we mean, right? Right. Okay. The kernel of L. Right. Well, you'll see that this set will have a particular meaning in quite a lot of contexts, so it's not for nothing that we have defined it. Right. Well, this set image of L, which is just defined as the image, usual, right? It's just a set of all W in W such that W is image of an element of V, right? And the proper notation for that would be actually, well, there exists the element V such that W is equal f of V. So this condition that defines this set, this is actually written like this, probably not like this, but you understand what I mean, right? Okay, it's called And from now on, sorry, of course not F. We have any F here of L. And from now on, we will omit bilinear maps such evaluation, and we will write them just like before the vector to which they are applied. It's a common convention that we do because, as we said, we will later identify the maps with matrices, and so this is uh, one has this idea in mind when one writes it. It's like multiplication of a linear map with a vector, but of course we mean evaluation and this vector, right? Okay, it's called image of L. Oh, let's prove a little theorem, and that's not the theorem that I meant. I'd like to arrive at in this session. That is a theorem, or maybe we should call it a lemma. It doesn't deserve such a big name, but let's prove it anyway. Well, what are the basics? Kernel of L is sub-vector space, and I'll explain in a minute what that is. Sub-vector space, and for short we call such structures subspaces. It is clear that it is sub-vector space in such a context. It is a sub-vector space of course, V, right? Image of L is sub vector space of W. So you see it is some kind of subset, but a subset with special properties. Maybe you can guess already what properties, maybe not. L is injective, really useful characterization. Is injective if and only if the kernel of L only contains the zero vector. Only contains the zero vector. Of course, it does contain the zero vector because, oh, we'll see why. Alright, and do we need something else? Well, I don't think so. Okay, something, the other things we will derive from neutralizes, okay? So, well, let's, yeah, first we should clarify what exactly is a subspace of a vector space. Well, for that we need a definition. And this is like just addition, right? Definition, subspace given a vector space V and a subset U of V we call U a sub-vector space, or for short subspace of V if U is itself, and recall we always talk about k vector spaces with same k. K is now fixed. If U is itself a vector space, a k vector space. Okay, vector space, but this is always k vector spaces, so we don't need to specify that explicitly, but okay, why not? Okay, well, and here we show short lemma for that, lemma characterization of subspaces. U is a subspace of V is valid if and only if all three properties hold. U is not empty, but these three properties are much easier to prove usually than the characterization, than the definition, easier than to check the definition. U is closed under plus. Of course, we mean plus in V, right? It's a subset of V, and it is supposed to be a vector space. Of course, we always mean implicitly a vector space with same operations, right? They're certainly defined on that because it is a subset of V, and the operations are defined on all vectors in V, and K is kept the same. So certainly, kernel multiplication is defined, and addition is defined. And it is even easier to see that the addition is defined, right? So, not under V, under plus in V, plus, but we don't write in V because it's obvious. We consider it as substructure, right? So it has to be same operations. You should also slowly but surely get used to such things that are just taken for granted that no one would specify actually. And under scalar multiplication, right? This is plus in V, scalar multiplication in V. Right, well, I guess that will be our first decent proof. Well, decent, I wouldn't call it decent, but at least I'll give this proof more or less completely. Well, we'll see about completely because it's too easy. But yeah, it will be our first proof. At least first thing that I call proof, I guess. Okay, doesn't matter. Okay, U is a subspace. Well, if U is a subspace, then U is. Oh, okay. Let's first we prove this direction. That is, we assume that U is a subspace, and we have to prove the three properties, right? Right. If we have that U is a subspace. Okay. I have forgotten something. We have to assume that it is not empty, or at least, well, let's just assume another thing. Always assume that this is a subspace U that contains the zero vector. Because otherwise we could have an empty set here, and empty sets, well, we could consider them as the general case of vector spaces, but we don't want to do that, so let's assume that. Okay, so then we have by definition that the element 0 is contained in U, and so have hence U is not empty. Yeah, you really have to assume that. So if you don't assume that, then nothing prevents me from saying, well, just take uh, an empty set, and an empty set satisfies its elements, satisfy all properties just by trivial considerations. So it would be a vector space, but yeah, the general case we don't want to have it right. So we have proved the first one. Now let's say have, right? Now U is closed under addition. Well, we see that U is closed under addition since it's assumed to be a subspace so in particular a vector space which is a particular vector space which later is a group and has closed under addition. As you can guess, U is of course analogously U is closed under scalar multiplication by same argument when recalling that U is a K vector space. It's just emphasis, right? Right. Because you see, maybe I should explain it a little more in detail because probably maybe you are not quite familiar with this kind of reasoning. You see, when we say that we have a vector space V and a subset U of V, and we talk about calling U a subspace of V if U is itself a K vector space, then what we mean is actually the following. It's just an explanation. Wow. U subset V subspace vector space is always meant, unless otherwise stated, is always meant as follows. V has, as we recall, some field K, it has some operation plus, it has some scalar multiplication dot, right? And U is also supposed to have such operations. We take exactly the operations from V for U, which means then U is equal UK. So we take same field. We take plus and dot, and they are not yet defined because they have to be defined on U. But I said they have to be the same as on V. What does that mean? Well, that means the following. The plus on U acts as follows. We just have plus on V, which we restrict to U. And then that acts on U indeed. And how does that act on U? Well, it does the following. If we apply plus U to some two vectors U1, U2, remember that's how we define the operations. The operations are just maps. And it is defined as V plus on V. We wouldn't write that, but let's write it just like with dots, right? We would have that. Which is okay, because this pair is in V cross V, so it is really defined. And that is just U1 plus U2. Here we write U0 plus on V. That's why we talk about plus just from V. We actually mean this restriction, right? Very important. Same with scalar multiplication. Scalar multiplication is restricted to K cross U, goes from K cross U. So where it is restricted to, therefrom it goes, right? Goes in U, and it just takes some lambda and it multiplies some element of U with this lambda, and this is an element of U, where this is again scalar multiplication in V. Scalar multiplication in V. Right. You see, that was just the explanation. All right. What do we have to prove next? Well, we have proved the three properties. We have proved that our subspace, if we assume that to be a subspace, then it is non-empty, that is closed under addition, and it is closed under scalar multiplication. Now do the more interesting part. Not interesting, but more interesting at least. Now we assume the three properties, and we have to show something more. There, by the direction that we just had, that was kind of trivial, like it was contained in the definition of the subspace, right? We didn't have to do basically anything. Oh, maybe you have to contemplate it a little bit, but other than that, there was no math going on at all. I don't exactly recall if there is some math going on in the other direction, but let's see, right? So, what do we have to prove? Right, have to prove, well, all the properties of a vector space. So, first, prove that U is an abelian group. That it is abelian, that is commutativity works on U when it works on V is trivial, right? Because we have just restricted that from V, and then for the application on particular elements, it retains all its properties, right? So now prove that it is a group. Right. Well, first we should prove, or maybe not first. Let's say. Okay. Not empty is just assumed. So yeah. Okay. Non-empty. You empty by assumption that we will need, right? So abelian check. Let's prove that it is a group of closed under addition. Check. It is just assumed. Now we'll just use that it is closed under scalar multiplication. Since we have 0, there is an element of U then above we have the assumption 3. U is closed under scalar multiplication. Then obtain zero is equal a minus a. You recall minus a is just actually this just means a minus a is a plus v vector minus a. And how do we know that this is actually in U? Well, we just apply the other property. We apply something like, okay, and now right, we apply that. Well, let me write it differently. We apply that. Minus 1, okay, in the field, which is of course in U because this is in U and this is element of U by assumption, right? This result is in U because it is closed under scalar multiplication. This is just a scalar in our field. This is just the inverse element for the 1 in the field within the field, right? So this is in U and the addition is closed in U, so this is element of U. Here you see that I kind of claim that in a vector space, it really holds generally, minus 1k is minus 1k multiplied by a is minus a. It is not obvious. It is not obvious. By the numbers, it would be obvious. Having just absolute definitions as above, you can't say that it is obviously like that. You have to show that, right? How do we show that? Well, we recall the definition. We just recall the definition. By definition, minus a plus a is equal to 0, or a plus minus a is equal to 0. So That is, minus a is defined by this property, and it is indeed unique. We could show that. We probably won't show that, but we could actually show that the I don't remember what it is called. Well, that the minus element to the element in a group, that it is unique, even if you assume in the definition not necessarily that it is unique, but you can then show the uniqueness. It follows some other axioms of the group, right? Yeah, but we could also assume that in the definition. But okay, let's check that minus 1k multiplied by a plus a is actually 0. That is to check. Well, how do we check that? We check it as follows. This minus 1k multiplied by a, and I mean, of course, that should give proper notation, plus a gives that plus that. Recall property of the vector space, multiplication by 1 doesn't change anything. Then we recall the distributive law on a vector space, right? One of the distributive laws, right? So, and this is equal 0, okay, multiplied by a. And from now on, I will drop the index k because, well, it's actually clear from the context, or you should learn to see things so that it becomes apparent to you from the context, just within your intuition, what belongs to what. So I will probably drop it, as it's completely unclear what 0 or what 1 is meant. And, well, you could be tempted to write something like this, right? This is, of course, 0 now in v, when u, well, actually, we don't know yet 0 u. We have to show that it belongs to there, so it's 0 in v now. Right? You could be tempted to write this and just think, well, in school we had that number multiplied by 0 is 0. But no, you can't do that because this now are abstract objects. It's not clear that something multiplied by 0 is 0, but indeed that's the case, and we'll show that. Well, proof. And is equal to k plus uk. That's just the neutral property of 0 in the field applied to itself, right? So this is distributive law in the vector space. And now we do the following. If we do same thing with equal things and nothing changes, you know it from equations with variables. Now we have something more abstract, but well, if we have something equal and we do equal thing with that, nothing changes, so we can just subtract on both sides. Okay, and that will give you 0, right? Because we just we actually add this vector that is the opposite vector to this vector, and here we add it, and we use associativity, and we get that 0 is equal. Okay, so indeed that's the case, and here we have 0 for 0. I said drop index, but it doesn't matter. This is 0 in V, right? Right, we have just shown that. Right, we didn't know what that is, but we have simply shown that with operations that are axiomatically well defined, that indeed 0 rises. Probably you have to get used to it, but for now, well, just try to keep up mentally, and you have to look at the whole picture and you'll see that it all makes sense. Right, but it's not easy. It's not easy. Right, where were we? Right, we have that, and with that, we have that 0 is indeed a new check. So 0v is a new, which proves what we wanted to prove, 0v subset of u. Right. Right. What else do we need to prove? Well, actually, all properties of a vector space, right? It's such a hassle, but okay, we'll do that, at least to some extent. Now, we have closeness under addition. We have proof that 0 is within, and if you look very closely at that, we have just proved that oh, oh, have just proved that for a given a in U, a is given, right? We can define minus a that way, and it is indeed in U, because U is closed under scalar multiplication, and this is just element in K, minus 1K, and this is element in U, right? Proves existence of the inverse element. Well, what do we have to prove for the group? Oh, clearly associativity is clear. As I told you, if we have just something applied to elements of a subset of some structure where the properties by such particular applications to elements hold, and those properties also hold by if we apply that to those elements when we only look at those elements taken from this special set. So nothing changes in how the operation behaves, right? Proves the existence of the inverse element. So we have proved that it is non-empty. We have proved existence of 0 in U. It turns out to be exactly the 0 in V. We have proved existence of the inverse element, and we have the associativity. So that proves that U is and abelian is for free, as I said. Associativity is also for free. Abelian group. All right. Then next we have to prove the properties of a scalar multiplication, but this is just, well, figure out yourself. It's really easy. It's just you have to recall something what I said, and you have to think about how things are defined and what structure relates to what structure, how, and how operations are defined, right? Figure it out yourself. Figure it out yourself. Why? Properties of scalar multiplication. Scalar multiplication. Vector space. Out. Scalar multiplication. By the way, because we use the field case in field, when you have to prove anything about a field, well, but that's of course the subspace has to be used as in field. And this sign that I made here is the sign that the proof is finished. If you are not familiar with that. Right, so we have proved this characterization of a subspace. Well, I did not expect that to take that long, but okay, we have to prove all the things and figures. Right, now we go back to our theorem, and we actually wanted to prove more advanced things, if you can call that advanced. Well, we wanted to prove that kernel L is a subspace of V, image L is a subspace of V, and that L is injective even only if kernel L is the zero vector. Right, and recall image is just the image taken pointwise, right, for all V and V. Right, image of each element in V is taken into the image of L, right? And the kernel was just the set of all vectors in V of exactly such that L maps V to 0 in W. Right. Okay. Okay. Right. Let's proof of a theorem. Let's prove a theorem. Proof of a theorem. All right. First, have to show that kernel is a subset of V. I mean subspace, not just subset, of course, subspace, right? So kernel L is a subspace of V. Oh, obviously, by definition, kernel L is a subset of V. Recall that it was defined like kernel L is such vectors in V, so it is subspace of V automatically. That LV is equals 0. Right, let's check. Secondly, no, that's not secondly, that's same point, right? Have L0 equals 0, and you see if L0 is equal to 0, then by this property that means that 0 is in the kernel of L. Because, of course, we can't just claim that, because, well, but that is very similar to what we already did. L0 and an exception, write it here properly, right? plus 0 property of a neutral element, 0 being the neutral element of a vector space. And this is very similar, like we proved above, where we have shown that multiplication with 0 gives 0. Actually, if you think about it, what we have shown was kind of the same thing as what we show now, because, well, multiplication by a can be considered itself as linear map. Right? It's a linear map that goes from our K to our vector space V, right? So, but didn't need to think about it. But yeah, that's just funny because same thing. So, and then you probably can figure out what happens here. We just subtract on both sides our 0 and obtain, well, the equal thing subtracted from the equal thing gives equal things, so that must be 0. So indeed, this property is satisfied here by 0, and that is why 0 is itself such an element of V, that is the kernel of L. Hence, what we had to prove here first, hence 0 is a kernel of a map L, right? All right. All right. Next, we prove the closeness. We use the criterion above, of course, right? And for application of this criterion, we just have to show closeness under scalar multiplication and under addition. So let v1, v2 be in the kernel of L. That is application of L to the v1 or v2 gives 0 respectively, lambda in K, and show that's the closeness. So L v1 v2 is equal to 0, L lambda v1 equals 0, and you can probably figure out that since those are just arbitrary elements, we don't have any restrictions on them, right? Could have taken just arbitrary elements. If this is arbitrary element, it suffices to just prove this for arbitrarily chosen elements, right? Have v1 plus v2. Just use linearity like above, right? By linearity, I was compatible with addition. Get that, and this is 0 since this is 0 since v1, v2 is in the kernel of L, right? It was how the kernel of L was defined. That the application of a map to an element of it is exactly 0, right? 0. W, of course. And L lambda v1 is equal, again, just use linearity. Use the kernel property, that is of course in V, and this gives that, and this is really sorry, that's of course W, that we really have a vector space that lambda multiplied by the 0 vector is 0, that you can prove yourself. We have proved something similar above. You can figure out how you prove that. It's really not difficult. Right, so we have that 0 is actually in it. We have that it is closed under, okay, maybe I should write it properly. So that implies, because we applied L to sum of V1 and V2 and we got 0, that implies V1 plus V2 is in the kernel as we wanted, right? Because we wanted to show closeness and addition, we took two elements from the kernel and we have shown that the sum of them is in the kernel, right? And this implies that lambda V1 is in the kernel of L, right? So we have shown closeness under addition, closeness under scalar multiplication, and we have shown above that 0 is in the kernel. Well, according to the lemma, this shows U is a subspace that's shortcut for subspace of V. Not U, sorry, kernel, but I mean by U now the kernel, of course. But I have not introduced that, so let's have not introduced that I call kernel U, so let's not use it. Okay. Oh, okay. That shows that. And this is first part of the proof. Let's do the second part. And the second part was what? Well, oh, maybe I should do it. Maybe I should let you do it because it's quite similar. It's actually even simpler, I would say. Just show that there is an element x in element V such that Lx is equal to 0 in W. We have to show that 0 is in the image, right? And for that we have to find an x that is really mapped to 0 by L. Show that f if W1 is equal f for V1 for some V1 and V, W2 is equal f of V2 element V, then W1 plus W2 is equal f for some element V. And show that, and this I want to spell out. You should understand what that is. Scalar multiplication. Closed under scalar multiplication. But what you have to show here, that you have to find out yourself. All right. Alrighty, that shows that, and of course I won't hide from you the third part of the proof. So let L be injective. If you recall, the third part is that L is injective if and only if the kernel is exactly the zero vector. So we have seen in the first part that the zero vector belongs to the kernel, but now we have to show, which will show the equality to the zero vector, or to the set containing only the zero vector of the kernel. For that, we have to show that there are no other vectors, right? The set got completely restricted to the zero vector. Not just zero vector is in it, but the set is completely restricted to the zero vector, right? So kernel L is subset of the zero vector. There are no other vectors in the kernel of L than the zero vector. And here, of course, we mean zero in V, right? And I mean the element, right? Not the set. It would not make any sense, but the element of the set zero is the zero in V, right? Well, how do we show that? What defines the kernel? The kernel is defined by the property that the evaluation at the element of the kernel is zero, right? Then now what do we have? We have f1. I just have subtracted on both sides. Okay, maybe I should not write it like that. It's rather physicist style, not ours. Okay, I should not insult all physicists, but many physicists, so physical technicians write it like that. I don't like that. We have to be proper. That is not meant as the approach. It's just thinking, right? Because it is in the kernel, that is equal to zero, because that is in the kernel, that is equal to zero, and that hence implies in particular that f of v1 is equal to f of v2, and then we can subtract it on both sides, and we get this is equal to zero, no matter if I write it left or right. Then we use linearity, and you should check that it really works by linearity. And here, since that is now, and you see that it is not quite obvious that it works by linearity. Plus works, but the minus is not just defined as something like in the school minus is something like plus. We can do all same things. Not quite. Of course we can, but you have to show that in this general setting that this is actually true. Of course it's true, but you have to show that. Right, and here this at 0 is equal to this. Implies. Oh wait, what did you want to show? Oh, we wanted to show, we had that this is injective, right? And now recall what injectivity tells us. By F injective, oh, I already write it down, and then I'll explain it. I'll read. By F injective, V1 is equal to equal 0. Right, wow, I have done a funny thing. I have to admit that I have done a funny thing. What did I do? Sorry, we don't need all of that at all. Much simpler. Okay, I'll write it down first and then I will erase that. Okay, well, that's what I mean, that I'll do it spontaneously. That's what I mean by, oh, maybe I'll erase it now. All right. We don't actually need it at all. All right, sorry. Uh, okay, that doesn't work quite well. Huh, okay. I didn't understand why. Okay, let's do it properly. Huh? What's happening? Okay. Okay, let's do it properly. Right. Okay, it's much easier. Sorry. Right. Let's. You probably already see how it works because I have written it down as a part of my my side jump, right? That v kernels L then L v is equals 0. Now L L of 0 equal L of v, where this is 0 as discussed above, implies that and this is supposed to be 0 and this has shown to be 0, so it is really equal. I told you that I won't write it like that because it's improper from the causal point of view, right? This implies 0 is equal v just by injectivity. If you recall, an injective function is a function for which we can't have same value for different arguments, right? If the values are equal and the arguments are equal, right? That is injectivity. Right, we just have that. Right, now let the other direction, we have the equivalence, to show, right? And we have them to show both directions. First we assume that and have shown that. Now we assume that and have shown. And have to show the other thing, right? And show that L is injective. Then have f of v1, f of v2, where v1, v2 elements of v is equal f of v1 minus v2. Okay. That's not what I mean. I'm too fast. Okay. Yeah, that's what I mean by spontaneously, right? I told you that I'm doing it just for my own pleasure, so don't expect anything specially prepared. Then have for one, the two, and d. Here we have to show the definition of injectivity, right? That it is satisfied such that f of v1 or f of v2 we have for that f of v1 minus f of v2 is equal 0, right? And that's of course same thing as f of v1 minus f of v2, and this implies, so we have that, and now that is equal to that, and so we have that is equal to that, but that implies directly that v1 minus v2 is element of a kernel. We don't know yet if it is 0, but recall that we have now assumed that our kernel is actually equal to 0 because we already have 0 is in the kernel, and we now have assumed that the kernel of L is not containing anything but the 0 vector. It is equal to the 0 vector, right? And that implies that 1 minus v2 is equal to the 0 vector, and that implies v1 is equal to v2, and hence started here f of v1 is equal f of v2, and we arrived at the conclusion v1 is equal to v2, which proves injectivity, right? This proves actually f is supposed to be L, of course. Yeah, right. We don't have any f. That's L, 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 right. This shows injectivity of L, so quotations together show kernel of L is equal to 0. Alrighty. Oh, that was long, but this was no fun at all, right? Alright, I guess today we won't arrive at interesting things, but okay. Well, we have proved the theorem about basic properties of linear maps. And next, I would like to do something fun, but I guess we'll need some things that I'll have to introduce first in order to do that. All right. Okay, let's see. Okay, how do you find that? And have proved as theorem. But okay, we have done it really rigorously, at least in the sense that we have written down everything. So of course it has taken a lot of time, and there were a lot of little explanations. So miracle, but yeah, I'd like to show you some really interesting stuff, but for that we'll need quite some notions. But let me formulate it, and let me introduce the notions in order so you can even understand what we are talking about. Well, next I'd like to show you the following theorem, also called dimension formula. And what dimension is, that we will discuss, but so that you know what abstract thing you have to look forward to, right? Dimension formula, how does that work? Well, let me recall that. Let's W be a linear map. VW finite dimensional vector spaces, that's basically vector spaces that we can handle pretty well. The numbers of elements and bases is finite, but for now you don't know what that means. Just write it down. We will discuss that in order. Okay. Finite dimensional vector spaces. And finally, some numbers enter. So dimension is one tool that allows to have some quantitative formulas about such abstract things like vector spaces, linear maps, and so on. Right. Then okay, that was that. Dimension of a vector space V is equal to dimension of kernel of L plus dimension of image of L. Right? So suddenly some numbers enter. In such an abstract system, some numbers enter because this dimension will probably be a number, you can guess. And well, dimension will be a number, but we don't know yet what number. And this we will look at probably later. But I'd like to show you another interesting thing. Figuring the set L the defined as L the L linear is itself a vector space. Itself a k-vector space. Recall that V is a k-vector space and W is a k-vector space. So we take any k-vector space V, we take any k-vector space W, and then the set of linear maps between the spaces is itself a vector space. Well, let's prove it, but I won't do all stuff that you have to do. It's quite boring. You have to do by yourself, but I'll do some things. Okay. Proof. Okay, define. You can probably guess how we would define it just from our examples of vector space. Define addition plus O1 plus O2 is defined as follows. And here you see how you actually define something like this. Oh, okay, you'll see some interesting methods of thinking which you will recognize later when it will become really interesting. So you have some vector in that and you just define it like that, right? It's just a definition, nothing else. Right. Okay. And well, you can probably guess how you define that thing. And this is this map. This is this map because we have to define it like a map, right? In order for that to be in it, it has to be a linear map again. So we just define how it acts in vectors because this is what defines a map, and its domain and its range are given, right? Or lambda is in K, of course. Lambda in K. Right, and this is in that W, and that is, of course, also for you clearly, and V is in V. Yeah. So with these operations, the W as a vector space. Well, as I said, I'll do some exemplary things, but I won't do it all. Let's get started. Okay, what do we have to prove in order for that to be a vector space? Well, let's do something more interesting, because it would be quite boring to prove it like that. Let's do a lemma. Let M be a set, V a vector space, then curly M defined as just all V functions. All V functions. I mean really all V functions. All V functions from M to V is a vector space. And here you understand that for functions to be a vector space, it actually only is important where the function gets evaluated, right? Because this is where the music plays, right? So you just see, well, define for f, g, I mean curly m, f plus g. Again, that's a function, of course, that goes from m again to v, not curly m, but just m. And it just maps f plus g maps the m to f of m plus g of m. And you see here already that what we define, it actually only depends on where we evaluate it. I mean, structural properties only depend on where we evaluate it, nothing else, right? Set V vector space K field. Again, any field. K field. Okay. Okay. We have to assume that it is a K vector space, because just not any abelian group would be already. Not any vector space over a field would be a vector space over every field, clearly, or no vector space would be a vector space over every field. So of course we have a K vector space. So, and then M is itself a K vector space. Right. Lambda. Okay. All right. And that is easy to prove. Right. Now you probably wonder why we started to prove this lemma. Well, you can just think about it. This is that above is just a special case where we have our domain V and not just some M, and we have W as our set of values, right? Which is indeed a vector space just by assumption, right? So we will be able to apply it in some way. Right. So abelian group. Well, do it yourself, but I mean, it's really boring. Show abelian group via. Oh, associativity. Clear. Because if you have f plus g plus h and you evaluate that, you see it only the music plays only in the value vector space. Nothing else happens. You just do pointwise evaluations just like you did with the vectors. It's nothing. Oh, I mean, of course, we have to show associativity. So of course we do that. So first we will always apply this function g plus h, and then we will apply the function g plus h to x, and then we will apply to that the function f plus g plus h. Right. Right. What I mean, we take g plus h as a function that results, and we will apply f plus g plus h to this x, which is just by definition, which we have given there, f applied to that, g plus h applied to that, right? Just g plus h is just the function in here, and you just have like a function from m to v, obviously, because it's defined like that, right? It's defined to be such a function. And with that, you just have that, and you have applied that, and this gave such result. And because you have associativity in the vector space V itself, clearly that gives you what you want. And now it is true for each x. That is, no matter what x you take, you always get the same. So this function has same domain, it has same space of values, and it is equal at every evaluation point. So of course the functions are equal because this is what determines the function, the domain, the space of values, and the evaluation at the respective points. If all evaluations are equal, then the functions are equal. So this is associativity. Commutativity is just the same. Yeah. Commutativity. In zero element or neutral element. Zero element, well, you can guess because we only act pointwise via the structure of V. That's just the function 0 that takes each m, that by the way x element m, right? Because we apply that to x element m. Consider that pointwise, right? This the separation functions. And this is just mapped to 0 in V, of course. So 0 element is just what pointwise will always add 0 to our respective functions. So f plus 0 somehow here, and that will be evaluated, and at each point this is 0, and so this will be f of x plus 0, right? And this will give f of x. Of course it's neutral element, 0 element, okay. Inverse element, well, you can guess. Inverse element minus f, which you could view as just minus 1k multiplied by f according to the definition above, or you could view it as taking exactly that, taking at an x minus f of x is just minus f of x. So at each x, you just take exactly that inverse vector to f of x. F of x is a defined function, right? You can take the inverse vector and each x, you assign to each x exactly this inverse vector of f of x, where f of x is already defined. So you can take the inverse vector, right? Inverse element is clear. And mind you, this is pointwise. So this is for each x in M, right? Pointwise or entry-wise, if you recall the identification of functions with vectors. Right, what is left? Well, I think, okay, well, what is left now? Okay, associativity, zero element, inverse element, commutativity, closeness, right. Well, closeness is obvious because we just define this function to be from M, and this is okay because we evaluated M and we just can evaluate that at each M is this is the well-defined group, right? So that's it. And properties of scalar multiplication. Scalar multiplication. Follow in the same way. You see, the structure that matters is only the structure of the value space because we just define the operations so that this is the only structure that matters just pointwise, right? And so of course it will work because it works pointwise in the vector space. We just like disperse the structure over all points, but we do exactly the same what we would do in the vector space V itself, right? So, well, so you have to believe me or you have to prove it yourself. It's no trouble at all. That shows that. So we now know that if we take any set and we take any k vector space and we consider all functions from this set to this vector space, just all functions, no properties at all. Then we will obtain a vector space. Those functions themselves will constitute a vector space. That's cool, isn't it? And now we'll see how cool it is. That is. And now you also see how our mathematicians use some tricks. Right. Back to the theorem. But VW. Now we know that the set of all maps, not linear maps, but all maps, F W, just F a map. I could write here F a map, but this is just obvious that F is a map here, right? Which set, of course, contains the set of maps with a particular property that L equal to W is a linear map. Is a vector space. Let's show, just to show that it is a vector space, we now have a useful lemma. We know what special kind of vector spaces can arise there, and this is subspaces. And we have a workaround to show that something is a vector space very easily if we actually show instead that it is a subspace. Of course, it does not always work, but often it is a good way to show that something is a vector space if it is immersed in a larger structure that also has properties of a vector space, and the operations are kind of the same. And it is a good way to show that something is a vector space just to show the characterization of the subspace, because then the property of being a vector space drops out automatically. Well, what do I mean by that? Well, then let's show that this, I called it L of VW. Let's show L of VW is a subspace of this set. Let's call it, I don't know, M again. So you should get used to it. I used this curly M above, but it was another context, and in that context we were finished, so I can use this letter again if it is clear what that means, and now it just means that, and hence it's clear, right? It is a subspace of that. So right, that was so. Okay. Well, first show 0 in M, actually. Oh, that time, let me write it down. So basically that says 0 is a linear map. Well, you can guess that if we always have that without a 0 and we have the special properties of 0 in neutrality, that will be the case. But let's check it quickly. So V1, V2, you recall that the 0 map was a special map that was just defined as 0, right? But okay, let me write it down quickly. And that was defined as being 0 in W, or here above 0 in our abstract vector space V, right? Okay, that is of course 0 W, right? That was the function 0M in this set that was applied to the respective vectors, and it gave respectively 0 W, because it gives that for any vector. And of course, same game here. This is just 0 in W, because that is a vector in V, and we apply that and we get always 0. This function is defined like that, and this is same as 0 D, because that is just 0 in W. Right, so hence 0 M element W, and with that we have some first property, show closed under plus, and so that we have just to show that the addition indeed yields again a linear map. Well, we just take L1, L2. Now let me write it properly, because that might be confusing in the beginning. We have 1, 2, So we take any L1, L2 from the space to show L1 plus L2 defined as always pointwise. That is how we define operations. Here, just the code. So, have for lambda element k, u1, u2, element v, that's L1 plus L2 of lambda v1 plus v2. That's by the way the shortcut to show linearity of some map A. You can just show, instead of showing separately A of the sum, so A is compatible with the sum, and then A is compatible with scalar multiplication, you can just show that this is 1 plus A true, because if you have shown that, then you can just take lambda equal 1, because you would have shown that for any lambda, right? If you have shown for any lambda. And this is compatibility with multiplication, just plug it in, and lambda and v2 equal the 0 vector, that shows the compatibility. This is compatibility addition versus compatibility with scalar multiplication. Right, so it suffices to show that. All right, let's look at what that is. Well, just by definition, that's lambda v1 plus v2. We just took this vector, we evaluate that it's the first map that participates in it, right? Or we evaluate the first map at that, right? And then we evaluate the second map, that, and now we have, of course, to use the properties of these maps to arrive at our desired conclusion, right? And the properties of this map, just like this, if a map is linear, then of course it holds, right? Because you can just use first the property of addition, and then you can first use in the first summoned, you can use the property of scalar multiplications, right? So that works, of course. v2 plus, okay, here I use that here as well, plus L2, v2. And now I'll just play around with those terms, namely use the commutativity. Recall that vector space is an abelian group. Now we are here in the space V, in the space W, right? Because we have arrived in W by these maps, right? So this object sign W, and now we just play in the space W. Play around here, I use commutativity, and I use associativity, and I use properties of vector spaces, right? Now, okay, that of course one, right? So I use okay, let's see, one, v1. Let me be a little bit slower. L2, v1. Here I just have used the distributive law on vector spaces, right? Here I as well, no, here I just use the, as I said, the commutativity, and I just use this associativity, right? The group property of the vector space W, right? And you recall that this now was by definition just L1 plus L2 evaluated at V2, and this was lambda, and here I use the definition again, right? L1 plus L2 evaluated at V1, and you can compare that with that for the map L1 plus L2, and can compare where we started and where we arrived, and you will arrive at the conclusion that if you replace A by L1 plus L2, we have gotten exactly what we wanted, right? So scalar multiplication. All right, next scalar multiplication, that probably will be homework, right? Show close standard plus, right? Closeness. That's even easier. You'll see here you won't have two maps here, so it's easier. You can do it yourself. Closeness and scalar multiplication. That's homework. Alright, with that, so we have shown that L of VW has a vector space. Alright. Thank you very much for your attention. Unfortunately, we have not arrived at amazing things I hope to arrive at. In truth, it always turns out to be a little lengthier or much lengthier than I suppose, and we do not manage to do a lot because there is so much stuff to explain with things that will get through it quickly, but it's important for me to explain things more or less properly, even though I think if you follow that, you have great difficulties, of course. I didn't doubt that. But it's just how mathematics is. You have to like mentally get into it, and there's no way of a king to learn mathematics, really. There's none. Okay, so let me look what we have here. Okay, we have done quite a lot concerning the degree of getting in G2, and we have managed. That's not a letter actually. Okay, well, whatever. At least I have written a lot. That's true for sure. Okay, well, see you then. Until next time.